half a degree or more per decade over wide parts of the Arctic. Over some parts of the Arctic, we have a reverse trend, but if you average everything out, there is a significant warming. If you then look at what we see in summer and what we see in winter, and compare these two pictures here with the annual average, you can see that most of the change is actually happening during winter. In summer, we hold the temperatures more or less constant because we have basically an ice bath. The sea ice is stabilizing the temperatures. So most of the change really happens during winter, most of the warming. If we are looking at that in a little bit more an abstract sense, where we plot on this axis the latitude from the high north to the equator to the high south, and here the time from 1890 to 2000, what we see here is that, and the color basically is the temperature. Red is warm and blue is cooler. So what we see is, if we sort of follow that thing, is that, yeah, there is quite a bit of variability. It goes from warmer to colder to warmer to colder to warmer. But if we sort of just move along that time scale, we can see that with all this variability, on average, it's getting warmer. And that is basically reflecting the 0.6 to 0.8 degrees Celsius warming on a global scale. What we also see is that at around 1940, there was, as part of a general warming cycle, this piece here, there was an amplification in the north, and it was pretty warm up there, almost the same or a little bit warmer in some parts compared to what we see today. What is different from in this period to the one that we are seeing today is that this was localized primarily in the north, and further analysis actually showed that this was a direction of warm air from the Pacific sector, whereas what we are seeing now is warming over the entire globe and within the Arctic over most of the Arctic region. So what we see here is a global phenomenon with amplification at high latitudes, whereas here we did actually have in the high latitudes a fairly specific feature that was localized in the Pacific sector. So then let's look at the ocean. If we are cutting through the Arctic from the Bering Strait here to France Strait, sort of across the center of the Arctic Ocean, what we see is here in a temperature section. Here's the surface. Here are the deep ocean basins at about 3-4 kilometers deep depth. That's quite a bit of relatively warm water, temperatures about half a degree to 1 degree plus, being pushed in from the Atlantic here, and then circulating around all the way around this basin, coming back out towards the Atlantic. This water, of course, would provide enough heat to melt the sea ice, would it not be separated by very cold water overlying it and sitting right underneath the sea ice cover. That is water that's right at a freezing point. And that preserves the sea ice cover. We are looking at the salinity. It shows here again Bering Strait and France Strait. It shows that at the top of the water column we have very fresh water that stratifies the water column and prevents that heat from mixing up and melting the ice. Now, during the 1990s, we had a unique opportunity to use nuclear submarines and crisscross the Arctic to see what had changed compared to the climatology. And here you can see along these tracks over the central Arctic, here is the Eurasian part, the Canadian part, Bering Strait, France Strait. The water right underneath the sea ice was more saline over the Eurasian part and a little bit fresher in the Canadian basin. And if we are looking at the temperature, we can see that the Atlantic layer warmed by up to 1.5 to 2 degrees Celsius. And what is not seen in that picture is that the core of the Atlantic water, meaning the heat source, moved closer to the ice cover. So what that does is it basically destabilizes the water column and provides more heat to the sea ice. Now, how does sea ice actually look up there, and how did it react to these changes? Here we have the mean ice edge in purple that was calculated for 2 decades, and then for 2002, 3, 4, and 5, you can see the actual sea ice edge here delineated in each of the figures, and you can recognize that large areas have been melted back. So if you look here, here, here in the East Greenland Current, over here, there's quite a bit of sea ice that disappeared. If we look at that from a satellite point of view and we compare 1979 to 2000, then again it's apparent that quite a bit of the sea ice in the minimum state has melted away. If we look at that in form of a time period, then we go from 1979 to 2006, and there is, as usual, quite a bit of natural variability, but there's also a trend which indicates that we are losing roughly 8% of the sea ice cover per decade. And if we are looking at the last few years, we had minimum years in 2002 and 2005. 2006 is a little bit higher again, but still sort of well within that trend line towards lower sea ice cover. If we are looking at the ice volume, the picture is even stronger. This is a projection by NOAA's Geophysical Fluid Dynamics Lab in Princeton, comparing the 1950s with 1 century later, 2050, and quite a bit of the sea ice has been lost in that particular model run, and other models point into a similar direction. And if we are looking how much of the sea ice volume really has been lost as a function of time, more than about half will be lost at that time of the simulation. So if we are taking the satellite observation of the sea ice extent together with observed and projected sea ice mass projections, we have to conclude that we are losing sea ice at a fairly rapid rate, and this sort of asks the question, or begs the question, is the Arctic moving towards a new seasonal sea ice free state? And the answer is probably yes. There was a recent publication that looked at all the possible feedbacks that are in the Arctic system, and the result of that study was that there are very few negative feedbacks, and that the Arctic right now seems to go along a trajectory that is fed by positive feedbacks and is moving towards a seasonally ice-free state, which we will see later will have quite a few implications. We are not just changing the sea ice cover, the ocean circulation, and the atmospheric temperature. We also have a change in river runoff. Specifically, there is, although with quite a bit of scatter, there is an increase in the Arctic river runoff. So there is more fresh water coming into the Arctic Ocean, from the Arctic Ocean into the North Atlantic. This is pretty well correlated with the increase in temperature, as we see here. And roughly, there is an increase of about 7,000 cubic kilometers per second per degree Celsius of warming. Now, coming to the Greenland ice sheet, which is by far the biggest freshwater reservoir in the north, which could, if melted, influence the salinity of the North Atlantic and thereby the thermohaline circulation that Wally has talked about. If we are looking at this picture, we can see that the area over which we are losing mass, meaning where melting of the ice sheet happens, is actually increasing, and you have realizations there from 92 and 2005, and you can see that the area is increasing rapidly. Also, there is quite a bit of movement along outlet glaciers, and they are retreating very rapidly here. 2001, 2, 3, this is movement of the edge of a glacier back towards the ice sheet.